Hi students, good morning. In our yesterday class, we are clearly learned about how to calculate atomic scattering factor, which is simply called as form factor. Okay, the form factor value, finally you get the result is form factor f is equal to 4 pi into integral 0 to infinity rho of r into r square into dr. This rho of r is nothing but electron charge density. So on calculation, you can take the crystal is the periodical arrangement of atoms. These atoms can be taken in the finite form. Especially that finite form is nothing but we can assume the atoms in the point-sized atoms. We can assume the atoms must be in point-sized atoms. For point-sized atoms, this complete form factor value is always be equal to atomic number, that is called as Z. Atomic number Z. Particularly, the assumed atoms must be in the point size. Point size is nothing but those are very tiny particles. On that way, that form factor value must be equal to atomic number. So, according to the intensity of diffracted ray, from lower classes onwards, nothing but intermediate point of view, intensity is always be proportional to square of the amplitude of the wave. Square of the amplitude of the wave. In this way, this amplitude of the wave, according to our calculation, finally you get this form factor value is directly proportional to amplitude of the wave. So on that way, intensity of the diffracted X-rays is always be proportional to square of the form factor. So I is always be proportional to square of the form factor. In simple way, you can take I must be equal to f square. I must be equal to f square. This is called as form factor. So, according to form factor, you can determine the clear intensity of diffracted rays. It is very necessary to calculate the waves are diffracted or not. Suppose that waves are diffracted, the intensity must be equal to square of the form factor. This value must and should be calculated by taking the crystal consisting of number of atoms. So the ultimate result must be depend on all atoms. In the crystal. Not only single atom in the crystal. It must be depending on all atoms in the crystal. So result must be depending on all atoms in the crystal. That means sum of all atoms diffracted beam of X-rays. With same wavelength, lambda and different amplitudes and phase angles. Nothing but pi. This is represented by capital A. So the ultimate result depending on the form factor, the result must be depending on all atoms in the crystal, not only depending on single atom, multiple, 2 atoms, 3 atoms, but not the. So it is always depending on all atoms in the crystal, that is sum of all atoms diffracted beam of X-rays. These X-rays have same wavelength but different amplitudes and phase angles. In order that this is represented or calculated by using vector form. This is also determined by using vector form. What is vector? The physical quantity having both direction and magnitude and obeys all vector additional laws. These three phenomena are obeyed, then the physical quantity is called as vector. Vector must having the magnitude. Second one is they have the particular direction, and third one must obey addition of vectors, addition law. These three are obeyed, then the physical quantity must be called as a vector. So this form factor value and dependent wavelength, amplitude and phase angles, these also are derived by using vector form. This vector form can be represented as the wavelength, the wave or length of the wave. Length of the wave is represented as vector length. Vector length with phase angle, phi. All are represented, different wavelengths, different amplitude, these are represented as vector length and with the phase angle of pi. So this is the form factor value calculation. So this value can be determined by using vector form also. Suppose we can consider a crystal consisting of number of atoms in the crystal. Suppose we can consider a crystal. We can consider a crystal. Crystal consisting of combination of atoms. So this combination of atoms I am representing the form factors. Those are F1, F2, F3, F4 for 4 atoms in a unit cell. 4 atoms in a unit cell. So F1, F2, F3, F4 are the form factor values. Those are representing 4 atoms for the unit cell. Their respective or corresponding phase angles can be taken as pi 1, pi 2, pi 3 and pi 4. Respective phase angles of form factors in the unit cell of the atoms. These are represented by like this. Suppose first form factor can be taken as, this is F1 with a phase angle of pi 1. Second form factor is represented by like this. This is second form factor F2 with a phase angle of pi 2. And third form factor I am taking like this. This is F3 with a phase angle of pi 3. And fourth form factor, this is F4 with a form factor of pi 4. So I am taking 4 form factors F1, F2, F3, F4. Those corresponding phase angles can be taken as pi 1, pi 2, pi 3, pi 4. For every vector is resolved into 2 components. For every vector can be resolved into 2 components. One is horizontal component, second one is vertical component. Like this. Already you know. Suppose this is a vector A bar making an angle horizontal with theta. Then this vector can be resolved into 2 components. That is along horizontal AX, along horizontal vertical AY. This horizontal vector AX can be written as A bar cos theta, and vertical component AY is represented as A bar sin theta. So this is horizontal component and this is vertical. In a similar way, these form factors are also a vector form. So every vector is resolved into two components. So what are those components? Along horizontal, this is f1 cos phi 1. In this way, this is f1 sin pi 1. In a similar way, f2 can be represented as f2 cos pi 2. In this direction, this is f2 sin pi 2. Next, f3. In this direction, f3 cos pi 3. This direction, f3 sin pi 3. f4. This direction, f4 cos pi 4. In vertical direction, this direction, f4 sin pi 4. These are the resolution of vectors, particularly form factor. The ultimate final vector of f1, f2, f3, f4 can be represented as like this. This is capital F bar. That F bar is called as, this F bar vector is resultant vector. Resultant vector of all form factors f1, f2, f3, f4. So this is simply represented by, this is horizontal component, this is vertical component. So this is horizontal component fi cos pi. This is fi sin pi. The resultant vector is, this is, that is f bar. That is f bar. According to the vector notation, that f bar value in a simple vector notation can be represented as the mod f bar square is equal to fi cos pi I whole square plus fi sin pi I whole square. Fx square plus fy square. Fx square plus fy square. So this can be taken as sum of sigma, because number of is there. So here also sigma. This is in the general form. In conjugate or complex analysis, from complex analysis point of view, it can be represented as f bar is equal to sigma fi into cos pi j, fi into cos pi j plus I into sin pi j. F star bar, their conjugate, fi into cos pi j minus I into sin pi j. This is with respect to complex analysis point of view. For these two equations, you can represent their product, f bar dot f star bar can be represented as f bar dot f bar is represented as sigma fi cos pi j whole square plus sigma fi sin pi j whole square. F into f star bar can be represented as mod f bar or f bar square. This value is always be proportional to intensity of diffracted rays. Intensity of diffracted rays. And this direction, particular this direction along the f bar direction. So intensity of diffracted rays is always be proportional to f square. This intensity direction always be direction along the f bar square. This is the calculation of form factor value. By using this value, you can easily determine the how many X-rays are diffracted. Suppose those X-rays are diffracted, what is the intensity of X-rays can be calculated. Intensity of X-rays cannot be calculated direct way, but in X-ray diffraction point of view, this intensity value can be calculated by depending on form factor. So first of all, you can calculate the form factor value. The square of the form factor value always be indicating the intensity of diffraction. That intensity of diffracted X-rays direction must be along the direction of form factor, value. So in this way, intensity of diffracted X-rays can be calculated. Particularly in our yesterday class, you can how to determine the form factor is completed. On the continuation part, today we are explaining that form factor value is represented by F. Intensity of the X-ray beam or X-ray diffracted rays must be proportional to F square. Particularly according to the vector notation, this is the vector notation. I am representing the 4 form factor values per unit cell. Per unit cell, how many atoms are considered? Here 4 atoms are considered. According to their atoms, form factors can be taken as F1, F2, F3, F4. This is vector notation I am representing. According to the vector notation, every vector must be resolved into 2 components. One is horizontal component, another one is vertical component. Where the angle is existed on that side, that is called as horizontal component. Horizontal component of vector is always be represented as cos term, and vertical component is always be represented as sin term. In this way, here you are observed F1, F2, F3, F4. So all horizontal components are along the right side. F1 cos phi, F2 cos phi, F3 cos phi, F4 cos phi. In this way, you can take the resultant of all horizontal components can be taken as that is horizontal component Fx is equal to F1 cos phi 1 plus F2 cos phi 2 plus F3 cos phi 3 and F4 cos phi 4. According to how many atoms are assumed, only you can assume 4 atoms. On that way you can take the 4 origin. Suppose in the crystal they have the infinite array of atoms. So in this way F1, F2, F3, F4 so on Fn. In this way this Fx can be represented as sigma Fi into cos pi. This I value 1 to infinity you can take. In a similar fashion F pi can be taken according to our notation. F1 sin pi is representing in the downward direction. See this downward direction. Second F2 is representing in the upward direction, and F3 is representing in the downward direction. F4 is representing on the vertical. So alternating or directions are in opposite direction according to our representation. In this way you can represent as Fy is equal to downward direction I am taking as a negative sign minus F1 sin pi 1 plus F2 sin pi 2 minus F3 sin pi 3 plus F4 sin pi 4. So in this way up to infinite number of atoms are there. Fi into sin pi. Here I tends to 1 to infinity. So according to the generalized I am writing, but according to our notation they get the alternate positive and negative sign. In this way the final vector, suppose you have the vector sum A bar is equal to xi cap plus yj cap. The magnitude of vector mod A bar can be represented as square root of x square plus y square. In that way, I am representing mod f square is equal to sigma fi cos I whole square plus sigma fi cos pi I whole square. So this is the resultant magnitude of the all form factor vectors in the periodical arrangement of atoms in the crystal. This is the ultimate final result. This result value always be depending on the all atoms diffracted by the X-rays. Not only single and double atom. Entire atoms are diffracted by the X-ray. The resultant magnitude of vector can be represented as f square is equal to sigma fi cos pi I whole square plus sigma fi sin pi I whole square. This is the generalized notation. In complex form, according to complex analysis, we can represent f bar is equal to sigma fi cos pi I plus I sin pi I, and f star, their conjugate can be taken as fi into cos pi I j minus I into sin pi j. So f bar into f star bar can be represented as f square. This value is sigma fi cos pi I square plus sigma fi. This value always be indicating the intensity of the diffracted X-rays. So the intensity of diffracted X-rays always be proportional to square of the form factor value. Square of the form factor value. For tiny particles, this form factor value always be indicating the atomic number. So this intensity simply is also represented as I is always proportional to Z square for tiny particles, or you can consider as the point atoms. You can consider as the point atoms. I is always proportional to Z square. According to form factor point of view, I is proportional to F square. This intensity value is always be along the direction of form factor value. This is the calculation of form factor or calculation of intensity of diffracted rays with respect to vector form. With respect to vector form. Okay. On continuation calculation, we can assume a crystal structure. We can assume a crystal structure. What is crystal structure? In our starting classes, you know the definition of crystal structure. You know the definition of crystal structure. So, what is the definition of crystal structure? Crystal structure is always be equal to basis plus space lattice or space lattice points. So this is the basic definition of crystal structure. Basic definition of crystal structure. Basis plus crystal. So according to the our crystal structure point of view, I am drawing the some lattice planes and bases. Some lattice planes and bases. So that is the crystal structure. This is represented by B1, this is A1, this is B2, this is A2. B1. So this A1, A2 are nothing but lattice planes. That is lattice plane. A2 is also the lattice planes, having the Miller indices are HKL. Here also Miller indices HKL, no doubt, HKL. And this lattice plane with respect to basis, the height of this lattice plane with respect to basis can be taken as P. Can be taken as P. And the distance between successive lattice planes, the distance between successive lattice planes is nothing but interplanar distance, that is D. interplanar distance, that is D. That value can be taken as D. So that is the representation of lattice. So the atoms of the basis in the plane B1. The atoms of the basis. What are the bases? Basis consisting of some lattice points and structure. The atoms of the basis are existing in the plane B1, B2, B3, so on, etc. The atoms of the basis are existing in the B1, B2, so on, Bn planes. In a similar way, the plane having the Miller indices are H, K, L. All planes are parallel family set of planes. Family set of planes have equal Miller indices. Those are H, K, L are the Miller indices. So the set of parallel family lattice planes have all having the same set of planes having Miller indices are H, K, L. So basis atoms are existing in the B1 plane, B2 plane, B3 plane, so on, Bn plane, and their lattice, their Miller indices can be taken as H, K, L. Their Miller indices H, K, L. The height of the lattice plane with respect to basis can be taken as D, and we know that the distance between successive lattice planes can be taken as interplanar distance D. So suppose you can instand on the X-rays like this. 1, 2. These X-rays are diffracted. They can create the phase difference. They can create the phase difference between the refracted by the A1 plane and A2 plane. That phase difference can be represented as the phase difference. The phase difference pi value can be represented as 2 pi by D into P. The phase difference between the reflected beam of X-rays by the A plane and B plane can be taken as phase difference is equal to 2 pi by D into P. P is the height of the plane with respect to basis and lattice planes, and D is the interplanar distance. Suppose you can assume one atom. Suppose you can assume one atom at jth position. Their coordinates can be taken as xj, yj, zj. Their coordinates can be taken as xj, yj, zj, and their Miller indices of the plane can be taken as h, k, l. So those are the positions and Miller indices. At that point of view, the height of the plane between the A and B can be represented as with a lattice constant. P is equal to H A into H into Ij plus K into Yj plus L into Zj divided by square root of H square plus K square plus L square. Square root of H square plus K square plus L square. This is representing in the calculation of Miller indices point of view and distance between successive lattice planes. D is equal to 1 by square root of H square by S square plus K square by B square plus L square by C square. On that way you can represent it. So P is equal to A into H xj bar plus K yj bar plus J zj bar by square root of H square plus K square plus L square. So each and everyone knows A by square root of. We know that according to Miller indices calculation, we know that A by square root of H square plus K square plus L square value is equal to D for cubic crystal. Why you are taking this way? For cubic crystal, A is equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees. General D value is 1 by square root of h square by a square plus k square by b square plus l square by c square. This condition is substituted in this equation. We get d value is a by square root of h square plus root of h square plus k square plus l square. This value substituting in this height of the plane. This value substituting in the height of the plane, we get P is equal to h into xj plus k into yj plus l into zj. A by square root of h square plus k square plus l square is replaced with d value. So that height of the basis to the lattice plane can be represented as P is equal to h xj plus k yj plus l zj into d value. This value is substituted in form factor value. This value is substituted in form factor. What is the value of form factor? You get the form factor f bar. F bar is equal to sigma fi into cos pi j, sigma fi into cos pi j whole square plus sigma fi into sin pi j whole square, sigma pi j whole square. This is mod f bar square. So you can substitute it in pi, you can substitute it in this pi. P is equal to xij plus k yj plus l zj into d. You can substitute it on that equation. You get the result is already know pi value is nothing but phase difference. Phase difference you ought to how to write pi is equal to 2 pi by d into p. 2 pi by d into p. In place of p you can substitute it 2 pi by d into p is nothing but x h into xj plus k into yj plus l into zj into d. D get cancelled. Then phase difference pi is equal to 2 pi into h into xj plus k into yj plus l into zj. This is the phase angle. This phase angle is substituted in form factor. You get f square is equal to sigma fi into cos pi is nothing but 2 pi into h xj plus k yj plus l zj whole square plus sigma fi into sin 2 pi into h xj plus k yj plus l zj whole square. This is the form factor value. By substituting their phase angle. We get the result is so here sigma fi cos 2 pi into hx plus ky plus lj whole square plus sigma fi into sin of 2 pi into x hxi square plus kyj square plus lzi whole square. On calculating we get the result, that is the form factor value. Suppose you can consider the crystal structure is, you can consider the structure of the crystal. The structure of the crystal is BCC, body centered cubic structure. For body centered cubic structure, how many lattice points per unit cell? Number of lattice points per unit cell. Number of lattice point per unit cell in BCC structure is 2, only 2. One is exactly center of the body, 8 corners are occupied by 1 by 8 portion, then 1 plus 1 is nothing but 2. So number of lattice points can be written as 8 into 1 by 8 plus 1, nothing but 1 plus 1, totally you get 2 lattice points. According to 1 is existent at corner, 1 lattice point, 1 lattice point position can be taken at origin 0, 0, 0. Second lattice point position is occurred at 1 by 2, 1 by 2, 1 by 2. Second lattice point is occurred at 1 by 2, 1 by 2, 1 by 2. These positions can be substituted in form factor value. You get the result is, suppose x, y, z zeros, 0, 0, 0, 0, cos 0 value 1. It's nothing but f1. Next 0, 0, 0, sin 0, 0. So ultimately first position can be represented as this only f1. Second 1 by 2, 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 1 by 2. Okay, 2 get cancelled, cos pi value minus 1. So 1 by 2, 1 by 2, 1 by 2, 2 cancel, cos 1, sin 180 value 0. So ultimately you get the result is, ultimately on substituting this position in form factor, you get the result is f square is equal to f1 plus f2 into f1 plus f2 into cos of pi into h plus k plus l whole square. This is the final form factor value when the crystal structure can be taken as simple cubic structure. The crystal structure can be taken as simple cubic structure. Sorry, simple cubic. Not the simple cubic, that is body centered cubic structure. For body centered cubic structure, the form factor will get f square is equal to f1 plus f2 into cos pi into h plus k plus l whole square. That is the final form factor value when the structure can be taken as body centered cubic structure. Body centered cubic structure. Body centered cubic structure. This is. So based on this equation, you get the final result is f square value is equal to f1 plus f2 into cos pi into h plus k plus l whole square. By depending on the value, that what's the value, h plus k plus l value, you get the result is even, sometimes you get the result is odd. Suppose you can take the plane is 101 plane and 111 plane. H plus k plus l value is 1 plus 1 plus 1 is nothing but 3. 1 plus 0 plus 1 is 2, and here h plus k plus l value is 1 plus 1 plus 1 is nothing but 3. Depending on the plane, the sum of the Miller indices may get even value, otherwise odd value. Even or odd value. Suppose you get the result h plus k plus l is even, then I value is maximum. The intensity of diffracted value is maximum. Suppose you get the result is odd of sum of the plane of the Miller indices, they get the intensity of diffracted rays is minimum. That value is f1 plus f2 whole square, and minimum value is f1 minus f2 whole square. So At what condition intensity of diffracted rays is maximum and minimum depending on the Miller indices sum is even or odd. Suppose the Miller indices sum is even, the diffracted X-rays will get the maximum value, and the value is odd, they get the diffracted intensity value is minimum. So I maximum is nothing but F1 plus F2 whole square. I minimum value is F1 minus F2 whole square. Some of the times they are asked what is the ratio of I maximum to I minimum. I maximum to I minimum. I maximum is nothing but F1 plus F2 whole square divided by F1 minus F2 whole square. That is I maximum by I minimum value is equal to F1 plus F2 divided by F1 minus F2 whole square. This is the ratio of maximum and minimum intensity of diffracted X-rays. So that is the maximum and minimum intensity when X-rays are diffracted through the given crystal. So the diffracted X-ray beams always be depending on form factor value. Once you know the form factor value, then immediately you can calculate the intensity of diffracted X-ray beam. That intensity of diffracted X-ray beam always be proportional to square of the form factor. Suppose the crystal consisting of particles can be considered as point-sized object. Suppose the crystal is nothing but combination of point-sized atoms. Point-sized atoms. This form factor value is always be proportional to their atomic number. The form factor value is always be proportional to their atomic number. Nothing but intensity is always be proportional to F square, and intensity is always be proportional to Z square. In terms of amplitude, intensity is always be proportional to square of the amplitude. This is the with respect to crystal structure, with respect to light and wave topic also. In terms of light and waves, intensity is directly proportional to square of the amplitude. In terms of crystal structures, particularly solid state physics, intensity value is always be directly proportional to square of the form factor. So you can consider the point-sized atoms in the crystal, that intensity value is always be proportional to square of the atomic number. Square of the atomic number. This is. So how to calculate the intensity? Intensity of diffracted X-rays cannot be calculated directly. First of all, you know that intensity of the diffracted X-rays cannot be found or calculated or determined directly. In alter way or in indirect method, you can calculate the intensity of diffracted X-rays by you can calculate the form factor value. You can calculate the form factor. The form factor other name is called as atomic scattering factor. Atomic scattering factor, otherwise scattering factor, otherwise form factor. So form factor, once you form factor value is calculated, the square of the form factor is nothing but intensity of the form. Intensity of the X-ray diffracted. So you can take the crystal, you can instanding on the X-rays, on the lattice point, the X-rays are diffracted. Suppose the X-rays are diffracted, they can get the peak values. Sometimes highest peak, sometimes lowest peak. The highest peak value get the maximums, and the lowest peak values get the minimum value. The lowest peak value get the minimum. So maximum intensity and minimum intensity is occurred with respect to peak values. So when the X-rays are diffracted, the intensity graph consisting of peak of the curves. The intensity graph consisting of peak of the curves. Alternate maxima and minimas are occurred. With respect to maximum intensity, F1 plus F2 whole square. With respect to minimum intensity, F1 minus F2 whole square. So once the X-rays are diffracted, the intensity get the peak values. Once the intensity get the peak value is nothing but at that condition crystals are diffracted by X-rays. According to this complete derivation point of view, the ultimate analysis they can give the result is all crystal structures otherwise systems obeys the diffraction phenomena. Each and every system of the crystal must obey the diffraction phenomena. So this form factor phenomena must be applicable for every crystal system. This form factor calculation or the form factor in calculation or phenomena must be applicable for each and every crystal structure, every crystal systems in the nature. No one not obey the system. Each and everyone must obey the form factor phenomena, otherwise scattering factor. So once you know the scattering factor value, immediately you can calculate the intensity value. Immediately you can get the intensity value of the diffracted X-rays by the crystal. In this way, you can easily determine the structure of the crystal and easily know when the X-rays are inciding on the crystal, those X-rays are diffracted or not. Easily find out. Once the X-rays are diffracted, they get the peak values of the intensity. Once peak values are getting the intensity, that condition is nothing but on that position X-rays are diffracted. Easily you can announce that one. So there is no peak values are observed on the condition diffraction is not takes place. But entire the nature, each and every solid or each and every crystal must obey the diffraction phenomena. Those diffraction phenomena is obeys on that condition. This form factor value is 100% is obeyed. So the structure factor is valid for all crystal systems in the nature. The structure factor is always be obeys and valid for 100% for crystal system, not only for one system, not only for two system. For every crystal system must valid for form factor or structure factor phenomena. This is the calculation of intensity of diffracted X-rays. This is the calculation of intensity of diffracted X-rays. Okay, very easy. In past, nothing but before class and today class, combination is nothing but one complete phenomena. What is that phenomena? That is called as diffraction intensity. How the diffraction intensity can be calculated? First, the diffraction intensity cannot be calculated by direct method. Directly you cannot calculate the diffracted intensity. How the intensity of diffracted rays are calculated? By using crystal systems in the solid state physics, you does not calculate the intensity in the direct way. According to in intermediate degree point of view, you does not calculate the intensity in the direct way. How the intensity can be calculated? In waves and light point of view, intensity can be calculated by using amplitude. Of the waves. By using amplitude of the waves, on that way you can easily determine intensity is always be proportional to square of the amplitude. In light and waves point of view, intensity can be calculated not in the direct way. In indirect method, intensity is always be proportional to square of the amplitude. In this way, this method is applicable for each and every condition. In a similar way, in solid state physics and particularly in crystal structures, once the diffraction is occurs on the crystal, the intensity of diffracted rays can be calculated by form factor. Otherwise scattering factor, otherwise scattering factor, otherwise atomic scattering factor, atomic scattering factor, otherwise this is also called as structure factor, structure factor. So the intensity of diffracted rays can be calculated by using structure factor. So once you know the structure or form factor value, easily determine the intensity value. How the intensity of the diffracted rays can be calculated? The intensity of the diffracted rays is always be proportional to square of the, always be proportional to intensity of diffracted rays. I value is always be proportional to square of the form factor, square of the form factor. Once you know the form factor value, easily determine the intensity of diffracted rays. So the diffraction intensity is calculated by calculation of form factor value. So yesterday class and today class completely we can clearly explain about how the form factor value is calculated. Up to last class I am showing or I am deriving form factor value, how the form factor value is calculated with respect to, you can consider the crystal. So finally you get the form factor value. On yesterday class you get f value is equal to 4 pi into integral 0 to infinity rho of r into r square into dr. So on yesterday class you get the result is form factor value expression is f is equal to 4 pi into integral 0 to infinity rho of r into dr. This rho of r is nothing but charge density per unit volume. Per unit volume you can take the charge density, particularly charge density of the electron in the crystal. R is nothing but position vector. Depending on this one, I am calculating the complete form factor in the, you can assume the vector rotation. In this way, you can convert it into vector form. Vector form. This vector form point of view, you can calculate the form factor value, capital F bar. You can get the vector form resolved into horizontal and vertical component. So the horizontal and vertical component point of view, the form factor value F bar is, or mod F bar square, you get the result is sigma Fi into cos pi j whole square plus sigma Fi into sin pi j whole square. In both normal form and conjugate complex point of view, finally you get the square of the form factor value is equal to sigma Fi pi j bar square plus sigma Fi sin pi j bar whole square. In this way, the intensity value is always be proportional to, intensity value is always be proportional to square of the form factor. Once the form factor value is calculated, you can take the square of the form factor. The square of the form factor value indicate the diffracted X-ray value. The diffracted X-ray values. The diffracted X-ray values. In this way, you can calculate the form factor. Particularly on the calculation, I am clearly explained about up to this xi is proportional to f square. After completion of this structure, we can take the one of the crystal example, and take the one of the crystal structure can be taken as body centered cubic structure. Body centered cubic structure. Body centered cubic structure is nothing but BCC. For BCC lattice, how many lattice points are there? 2 lattice points are there. Particularly, you show the diagram also. Like this, every corner occupied by 8 lattice points. For every atom, 1/8 portion is occupied per unit cell. Particularly at the center of the body, they are occupied by 1. Nothing but 1/8 into 8 plus body center. So 1 plus 1 is nothing but 2. Suppose you can consider this v is taken as origin like this, x point, y, z. So first point, this complete lattice point is existed at the origin location, and body center location is existed at 1 by 2 comma 1 by 2 comma 1 by 2. Along that way, they have the phase difference is represented by pi value is equal to 2 pi by d into p. D is nothing but interplanar distance, P is nothing but the height between the basis and lattice plane. Basis and lattice plane. So I am representing basis in the circle and the planes are represented by dot pointer. The height of the basis from the lattice planes can be taken as P, and lattice point to lattice point distance can be taken as D. On that way, you can P is represented by, according to the Miller indices of the parallel family set of planes is HKL, this P value can be represented by 2 pi by D into H into xi plus k into yj plus L into zj. Here dd get cancelled, then finally you get the pi value